talk will be about another application of sparse partition, this time in the streaming setting. The joint work with several great collaborators, Arthur, Arnold, and Robbie, and Xiaofeng, and Mingwei. Okay, so it will be about facility allocation, which is kind of a clustering problem. So start by introducing it, because it's not at a distance, so let me define it. So we have a point set in some high-dimensional space, and I will be talking about Euclidean space and opening cost, something like here. And we would like to open a set of facilities to serve these points, like clients. Let's say these are clients, so we open some facilities. And we would like to minimize the cost, and the cost has two parts. The cost of connecting the clients to the facility, and also the cost of actually opening the facilities. The connection cost is given by the Euclidean distance to the closest facility. Yeah, so maybe like here for this very dense cluster, it's lots of clients. We open a facility. And there are some kind of separate points that are far away from everything else, so it actually makes sense to open a facility also here. So as I said, this is a clustering problem. It's kind of similar to K-median, but with a variable number of centers. We can basically pay for more centers. And as this opening cost, and basically kind of by scaling, you mostly can just think of a unit facility cost. So I will be using unit facility cost in this talk. So we would like to solve this problem in the streaming setting. So let me define it. So now the input is given as a sequence of points from this high-dimensional space, and we can scan through this sequence just a few times, just one time ideally, and we cannot remember everything. Like we have memory. Like logarithmic memory, let's say, or polylogarithmic, and we would still like to say something about this problem. The first observation is actually that we cannot really compute the full solution, because it can have n-half facilities or something, and storing the solution out of space. So we're just interested in estimating the cost. It basically says, let's say, how well clusterable the instance is. So we would like to compute some estimate that's a constant factor approximation with high probability. Okay, so actually we work with a slightly more general model of dynamic streams, where we allow also to delete some points. The classical model introduced by Piotr Indyk 20 years ago. And here actually the points need to be from a discrete grid, some kind of a finite precision, and the space will depend polylogarithmically on the precision. But actually, for the purpose of this talk, you can just think of these insertion-only streams without deletions, and we make a slightly incorrect claim. And then if sometimes if you happen to design a nice algorithm for insertion-only streams, let's say based on sampling, you can kind of extend it to handle deletions with some more work. Not always, but will be the case here. Okay, so distinction between insertion-only dynamic is not very significant for this problem, let's say, but the distinction between the low dimensional spaces and high dimensional spaces is significant. So basically, low-dimensional spaces defined as allowing to use space that's exponential in the dimension. So maybe you can think of a constant dimension. And whereas in high-dimensional spaces, this would be like too much space for the algorithm. So I only allow polynomial space. So of course, it's much easier to deal with low-dimensional spaces. There are already lots of results. I will not go over in detail. Let's say some constant approximation, especially for facility location. There's an approximation scheme. And the way how you typically approach the space, that you partition it somehow using some grids, let's say randomly shifted grids, or quadtrees, which give you the embedding, and that you can use to design your algorithm. However, it's much more challenging in high-dimensional spaces, and kind of still don't know for many problems how to get constant approximation with small space. And now small means like polynomial in dimension and polylogarithmic in n. Okay, and for the high dimension, you can think of as being logarithmic in the number of points. You can get to that by using dimensionality reduction, standard. Okay, so I say that there's a lack of technique for constant approximation. That there are several exceptions, like actually the k-median, but only for small k. There's also very nice result for max cut, and yeah, there are more results in insertion-only streams, but I don't want to really go into details. So maybe after that. Okay, so what can we do for this facility location? As I said, in low dimension, we can do a lot. Actually, the first work by Indik already proved polylogarithmic approximation, but with small space, using quadries. And then people focus on low dimension, so space exponential in D, and eventually gave 1 plus epsilon approximation. So the question was, what can we do for high-dimensional spaces? And we wanted to give constant approximation, polynomial in the space, ideally in one pass. Okay, we actually failed, but we can do something at least. We can relax kind of any of these three conditions on the number of passes. So if you relax the number of passes, then in 2 passes over the stream, we can give constant approximation with small space. We can actually compress the 2 passes if the stream has a random order. And then it makes sense to talk about insertion-only streams only. So if we relax the approximation condition, then we can have just 1 pass, but the approximation will be like D, but the space will be small. Or we can get to constant approximation in 1 pass, but we need to space some more space. It will be actually small polynomial in the number of points. So these are like kind of 3 results. I think these 2 below are the most interesting and most involved. There's actually a smooth trade-off from this result to the last result. Okay, so maybe you can ask, so how far can we get? My answer is that I pretty much don't know. So the only thing that we can prove is that some small constant approximation will require space exponential in D, which is using communication complexity. So maybe I will get into some details at the end. Okay, so how do we design actually algorithms for facility location? There's actually a very nice tool from previous work from the method-Plaxton approximation algorithm. And the tool is that we can kind of decompose the optimal cost into individual contributions of the points at the instance. So for every point, we define kind of a radius so that the sum of these radii is roughly the optimal cost. And the second property is that if you look at, like around some point, if you look at a ball of radius rp, the number of points inside this ball will be roughly 1 over rp. So yeah, here's like a point that's well separated from everything else. So it has rp equal to 1. These two have 1/2. And a very dense cluster of many points has all points inside have very small rp values. And intuitively, like you can serve this very dense cluster with just one facility, paying 1, and the connection cost will also be small if the points are close enough. Let's say they are even collocated. So the formal definition of this rp value, there are in more ways how to define it. That basically you define it so that this roughly holds. So take the minimum radius such that the ball around P of radius r contains at least 1 over r points. And then actually proving this this property is more involved using this Metuplex approximation algorithm and some charging arguments. Okay, so now our goal is to actually estimate this sum, and this is sufficient up to constant factor. Yeah. And you know, if you think about the second property for a while, you can derive a simple streaming algorithm, low space streaming algorithm, that gives constant approximation of RP for any point P I can give you. But I need to give you this point at the beginning, right? So what I do just is that I make concentric balls around this point, and I count the number of points inside these balls. And you know, I take the smallest radius when this exceeds 1/r. Okay, this is great, but P is given in advance. Now the bad news here, and it's also not difficult, if you don't know this P in advance and you want to somehow process the stream of points and then estimate RP for a point P given as query, you need kind of a lot of space, even like you need to basically store everything if you want constant factor approximation. Okay, so so this somehow says that you know, so what we actually take as approach is that we will sample some points from the stream and then estimate these RPs. But you know, given this lower bound, maybe we should just aim for 2 passes. So that's what we do. So we would like to, in the first pass, somehow sample points, and you know, it's a priori not clear how to do it. So let's just start with uniformly sampling a few points. And then in the second pass, estimate their RP values. Okay, so now maybe if you stare at this instance for a second, you may see what's a problem with this. Right? So let me define the instance more precisely. Let's say I have square root of n points which have large RP, and then the rest of points are basically in very dense cluster, which you know, you can serve very cheaply. So basically, the optimus cost is pretty much determined by these points of large RP, but there's relatively a few of them. So if you sample uniformly, you will most likely hit something here. So unless you sample square root of n points, you are just hitting something here. So that just does not work. Okay, so how to resolve this, right? So the way we resolve it is using importance sampling. Basically, we would like to sample proportionally to the importance of every point, and importance is just the RP value, which is the contribution of the point to the optimal cost. Okay, this will eventually give us constant approximation. And you know, a standard importance sampling, if you can estimate RP value for the sample point and also estimate the probability of sampling that point, then this fraction is an unbiased estimator of the sum of RPs. Okay, so now we would like to sample with probability proportional to RP, but in one pass, but we cannot even estimate RP for query P in one pass. So it's kind of a chicken versus egg problem. So how to resolve it? We resolve it basically by using the geometry, that we are in geometric space. So what do we want is that we like to partition the space, the high dimensional space, and then round the points to the buckets of the partition, so that we have much higher probability to hit a point of high RP. So for large RP, we would like to show that there are only a few points in the bucket of P. Whereas these dense clusters that we are hitting by uniform sampling a lot, we would like them to actually be mapped into just few buckets. If you think about it for a second, you realize this is pretty much what Arnold told told us about a few minutes ago. Okay, so yeah, we would like to have a space decomposition. There's bounded diameter buckets. That's for the points of large RP. They are kind of well separated from everything else. And for these dense clusters of many points, we would like them to intersect just a few number of buckets. So maybe just a side remark: if you just impose a grid or quadtree, this wouldn't really work, because like if you have a dense cluster around the vertex of the grid, it would intersect 2 2D buckets. That's too much. Okay, so let me go back to the definition of sparse partitions. So I made one slight change. We think more of it as a hash function. That's why we call it also consistent geometric hashing. It's really the same definition. Like the buckets of the hash function to have bounded diameter for some given L, like for any given L, and to have the sparsity property that any set of small enough diameter, up to this gap or padding parameter sigma, we would like this set to intersect small number of buckets. Right. So this is pretty much the definition that Arnold told us. Up to one subtle difference, we actually will need to compute this hash functions in streaming, so it means in load space, and we actually need to store it in load space. Okay, and here we have two parameters. I think for Arnold they had pretty much the same significance. For us, this sigma, this gap parameter, is actually more significant because it will affect the approximation ratio of the one-pass algorithm. So let me just quickly recap which partitions we can construct. Yeah, using kind of a random clustering process. It's called ball carving. Was used already to construct locality-sensitive hashing. We can get nearly optimal trade-off for Euclidean space. So for any given gap parameter sigma, we can get some tau that's exponential in the dimension, but divided by sigma. So we can eventually, like for large enough sigma, we can make it polynomial in D. So in particular, we can have these two like extreme points in this trade-off. We can get sigma D over log D, and tau will be polynomial in D. Or we can have like much smaller sigma, let's say constant. And if you set the dimension to be logarithmic, then tau will be like a very small polynomial in N. Okay. So I'll not go into details, maybe at the very end, how to actually define this. But yeah, basically it's a random clustering process that you keep adding the centers randomly, and like carving out balls from this cube. Okay, so it's a small caveat. This construction, the way we define it, it takes time, exponential time in the dimension to evaluate the hash function for any given point, which is a shame. So we have kind of a much simpler construction which has various parameters sigma, but you can evaluate the hash function in time polynomial in D. Okay, I will not go also into details. So let me show you how to use it actually. So this is our instance that was hard for uniform sampling. That was this then cluster, right? So now we impose this sparse partition or geometric hashing, and which means that this cluster is split into just a few buckets. And now if we sample a random non-empty bucket, then we are much more likely to hit a bucket with a point of high RP. Okay, which pretty much resolves this instance. Of course, reality is slightly more complicated than the nice instance, right? But not too much. Okay, so let me give you some details of this two-pass algorithm. So I like to estimate this sum, right? And I will just focus on estimating the number of points of very high RP, and you can reduce to this case, like if you want to estimate number of points with RP 1 over 2 to I, you can reduce to this case by just subsampling, not too difficult. So we impose this path partition as a form of hash function. In the first pass, we sample a non-empty bucket of this partition, and like from this sampled bucket, we sample a point. I will tell you in a second how. In the second pass, we estimate the RP for each sampled point using this counting of concentric plots. It's easy. So how do you implement the first pass, sampling pass? There's a tool, there's a nice tool that's called L0 sample or distinct sample that samples a uniformly random element from the support. Now our support are the non-empty buckets. Okay, that works, but so how do you actually recover this point? There's a nice trick. We actually make this sample of two level. On the first level, we sample the buckets. Now in the second level are also L0 samples. So kind of the first level sample samples a bucket and samples and L0 sample for this bucket that gives us the point. And the way why it works is actually that these L0 samples are linear sketches, and with some thinking you can make it work. Okay, so why does it work? The key claim is that there are not too many non-empty buckets after you impose these sparse partitions, and not go into the full proof, but the main thing is that if there's a point of, or for a point of very small RP value, like 1 over sigma, where this sigma is this gap parameter, that means that piece in a cluster with many points and a very small diameter. And now we can use the property of the sparse partition that it's clustered into just a few buckets. All of these many points are actually clustered to just a few buckets. That's it. So kind of a bottom line is that we can make the important sampling work in one pass. So we can sample with probability RP divided by something quite small, which is still sufficient. Okay, so now in random order streams, it's not too difficult to tweak the two-pass algorithm into one pass over random order streams. Basically, the first half of the stream is used for sampling, to simulate the first pass, and the second half of the stream is to simulate the second pass. And because it's random order, it kind of works. Okay, so we very briefly how to actually do it in one pass over arbitrary order streams, but with Weyer's approximation ratio. Okay, so the key insight is that like if there are just a few points around P, then RP must be large. So we would like to get to know how many points with large RP we have in our instance. So we do it using this observation, but just counting the number of points in each bucket is not sufficient, because there may be a dense cluster just next to this point, but in a different bucket. So we actually need to count a number of points in a small neighborhood. The way we do it is that actually we have a counter for every bucket, but when a point arrives, we increase not only the counter in this bucket, but also in all the neighboring buckets. So I have buckets like here, a point that arrives, so let's say this is its close neighborhood, so I increase the counter in all of these buckets. Okay, so this increases the support of the L0 sample, but not too much thanks to sparse partitions. I think skip the details. Yeah. So the point is that you need to make these neighborhoods small enough so that you don't increase the support of the sampling too much, and so you need to sacrifice this sigma parameter of the sparse partition that will translate into approximation loss in the approximation factor of the algorithm. Okay, so I will probably skip the lower bounds. I said it's just communication complexity exercise with some tweaks. Okay, so these are all results. I think it's a very nice open problem how to actually get what we wanted, and I would just conjecture it's possible because the lower bound, the way it's done, maybe you can increase the constant a bit, but basically you kind of try to encode a hard instance, let's say graph instance, into high-dimensional space. But if you encode a graph instance into high-dimensional space, the non-edges, so maybe like the edges correspond to distance 1 between the vertices, but the non-edges will correspond to distance, let's say, square root of 2 between the two vertices. So maybe you can make it square root of 2, but I don't see how to do it beyond that. So yeah, so that's our main technique. There are other open problems like this lower bound is for just one pass, or how to extend it to more passes, or maybe in more passes we can get 1 plus epsilon approximation even in high dimension. And yeah, as I said, our nearly optimal construction of sparse partition has this drawback of not being time efficient. So that's another nice open problem. Okay, so that's it. Thanks.
I'm just curious. You know, here you have all the results like independent of n in terms of the ratio. If you're willing to have n dependence, I guess you can get log n over log b ratio. But is that?
I see. I mean, you mean approximation.
Yeah.
So like maybe I didn't stress it. Here we have polylog factors in the space.
In polylog.
Yeah, but here, yeah, if you want, yeah. So d can be like logarithmic, right? So this is like about log n ratio.
I guess I was curious. Prior to your work, were there any other works that already kind of investigated the end? Like if you're willing to have n dependence, like what the best n dependence is?
Yeah. So there was this algorithm by
Indigo 4.
Indigo 4.
Indigo 4.
Square log n or something. So it's
log square or log cube.
Okay.
Yeah, maybe log cube.
Approximation.
Okay.
Right. Thanks. Yeah, so basically, in other words, this result improves from log cube to linear in logarithm.
Yeah, actually, I'm curious. I don't know if this was in the slides you didn't go through, but what is the Boolean hidden matching problem?
Yeah, so it's a communication problem. Alice gives like 2n bits. And Bob gets a perfect matching on the indices. And the promise is that either like all edges of the matching, actually if you make XOR of the 2 bits, you get either 1 on all edges of the matching, or on all edges you get 0. It's actually a slightly simplified version, but it doesn't matter. And using sampling, you can get like square root of n communication, and this is actually tight. So it means like Alice needs to send square root of n bits at least to Bob, so that Bob can determine which whether it's yes instance or no instance.
All right, thank you again.
Thank you.